everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In this class, we will study about transistor as in switch. Now first we will discuss what a switch is. The switching operation or the switching of a device is nothing but it on and off the electric current in the circuit. So it is nothing but a current provider to the circuit. If current is flowing inside the circuit, then we say it is on, and when current is not flowing in the circuit, we say that it is in off condition. So for the switching operation of transistor, we use common emitter configuration of NPN transistor. Now why we are using common emitter and NPN transistor? There are few reasons. First is common emitter configuration. In common emitter, we know that emitter section is common. Let's say if I roughly draw a diagram, this thing. This is our emitter side, this is base and this is collector. So emitter side is common in input as well as output. So this is our common emitter configuration. We use the common emitter configuration for switching purpose so that the current gain and voltage gain and the power gain of this configuration is maximum. Okay. Now we use NPN transistor. Why we use NPN transistor? Because the mobility of charge carrier, which is electron in NPN transistor, is higher than holes. So we use NPN transistor for the switching operation. Okay. Or we will do transistor as a switch in NPN transistor. Now we will discuss the circuit and operation of transistor as a switch. So this is the basic circuit of common emitter configuration. Here, this is the battery which is in variable in nature, and this is VBB, which is base biasing battery. And this is the resistance RB, which is nothing but the current limiting resistor in base section. Now here, this is the current limiting resistor for collector section, and this is the variable battery for collector section. So this is VCC. Here we can see that this is our emitter junction, which is grounded and common in both input and output side. This is our collector and this is our base. So here we consider this section is input and that one is our output. Okay. So we will draw the current here. So this is the positive terminal of the battery, this is the negative of the battery, and this is NPN transistor. So positive connected here P section and P, these both are N section. So positive connected, it means the base emitter junction is our forward bias. Similarly here the collector emitter junction is our reverse bias, because this is N side and it is connected to positive of the battery. So the charges are different. So this is our reverse bias. This section is reverse bias. Similarly, this section is our forward bias. This is the basic operation of transistor. Now we will discuss how the current is flowing inside the circuit. So we will discuss how current is flowing. Now here, from this battery, current is going in this direction. So this is nothing but IB, which is flowing in this direction. So this is the sign of current. So emitter current is flowing in this direction. And from this battery, current is flowing in this direction. So this is the direction of IC. This is the basic structure of transistor as a switch. Now we will do the circuit analysis of transistor as a switch. Now here we can see that this is our input side and this is our output side. So we will apply KVL in the input side. So in this loop. Firstly, from this resistor we are starting. So this is the positive flow of current. Now this is IBRB. Voltage drop across the resistor is IBRB plus this voltage, which is nothing but VBE, which is also in positive manner. So VBE. Here from this side, negative to positive we are coming. So this VBB is in negative. So negative VBB is equal to 0. So from this side, we clearly see that VBB is nothing but VBE plus IBRB. This VBB we can similarly consider as input side. So we can replace it with VI, which is nothing but input voltage. So this equation will be VI is nothing but VBE plus IBRB. Okay, because this VBB is nothing but connected to the input side and input voltage we are simply considering as VI. So this is our equation 1. Okay. Now we will apply KVL in the output loop. So this is our output loop. This. And we are applying the KVL. So current direction flowing in this direction. So voltage drop across this resistor RC is nothing but minus IC RC here, because current is flowing in this direction and battery potential is like that. and we will consider this voltage, which is nothing but minus VCE, and that one is negative to positive battery potential, which is plus VCC, is equal to 0. Here VCE we can consider as output voltage, because this is the potential here VCE, and this is also the also at the output. So we replace this VCE by V out. So V out is nothing but, here if we consider the value of V out, which is nothing but VCC minus ICRC. So this is our equation number 2. So from input and output we get two equations. First one is input Vi is nothing but VBE plus IBRB, and second one V out is nothing but VCC minus ICRC. So now these are the basic equations which we get from input and output loop. Now we will discuss it in little detail. So the first condition we have is Vi, which is nothing but the input voltage, is smaller than the knee voltage or the cut-in voltage for the transistor, which is nothing but 0.7 volt in case of silicon and 0.3 in case of germanium. Here we assume that we are using the silicon transistor. So 0.7 volt is our cut-in voltage. So when Vi or input voltage is less than 0.7 volt, what we will get? We will get IB equal to 0. If IB equal to 0, so IC is also equal to 0. Okay. So in this case, V output is nothing but, if IC is 0, so V output is nothing but VCC. So this is our first consideration, that output is VCC. Now the second consideration we have is, when Vi is, the second consideration we have is when Vi is greater than 0.7 but smaller than 1 volt. Okay. It means the transistor attaining the cut-in voltage, so it starts, but the value of the voltage is less than 1 volt. So in this case, what is happening? The output voltage is VCC minus ICRC. So in this case, IB will also increase, so that IC will also increase. Okay. Transistor is working, so IB, IC both are increasing. If IC increase, it means the value of V out is decrease. In this section, if IC is increasing, it is negative with VCC, it means the output voltage is decreasing. So this is our second observation, that if Vi is in between 0.7 to 1 volt, it means the transistor attain its cut-in, it start working, but it is in a window of 1 volt, 0.7 to 1 volt. So in this case, IC current is increasing and V out is decreasing. So we will plot these two in our graph. What is happening? This is our graph. This is nothing but Vi and this is V out. Okay. And this is our, let's say, 0.7 volt and this is our 1 volt and it is beyond 1 volt. Now what is happening? If the voltage is below 0.7, somewhere here 0.7 we have. So if it is below, then the output voltage we will getting is VCC. So till now we are getting the voltage is VCC. Okay. Till 0 to 0.7 volt, below 0.7 we are getting the voltage, output voltage as VCC. But in this window from 0.7 to 1 volt, the current is decreasing. Here we can see that from this equation, if IC is increasing, V out is decreasing. So V out is linearly decreasing when IC is increasing. So the decrement is like that. Okay. Current is decreasing till 1 volt. So these are the two parameters we discussed, that in first case Vi is below 0.7. So the current is the output voltage is nothing but VCC, and when Vi is in between 0.7 to 1 volt, the current is linearly decreasing. The current is linearly decreasing. Now we have the third case. Okay. Here we have the third case. We will do our third analysis. So third case, when Vi is greater than 1 volt. Now what is happening? So 0.7 volt it also attained, but it is greater than 1 volt. Beyond 1 volt, what is happening? In this case, IC saturate. Why so? Because IC has also some limitations. The current is nothing but the charge carriers, the flow of charge carriers, and in a particular silicon transistor, charge carrier are fixed. We know that I is nothing but any AVD. VD is mobility, NE is our electron and its number, and A is the cross section area of that plate. So If I is any VD, according to this, the current is fixed. It means it is not increased beyond a particular limit. So here IC saturate. When Vi attain a maximum value, IC saturate. It means IC is in its maximum value. Beyond that, it will not increase. So the last case we have considered it IC saturate. So IC is in maximum value. In third analysis, we see that IC is in maximum state. Beyond 1 volt, when Vi is reaching the limit of 1 volt, the IC is max. It means the voltage is minimum. So this is the value of minimum voltage, which is nothing but steady in nature, and it is not reached to zero because it has some value, but it is linearly it is steady. It is steady, and this beyond 1 volt, this transistor is acting in saturation mode. So there are the three modes of the transistor. First one we discussed, this where V out is nothing but VCC. This is our cutoff mode. In this, transistor is in off state and it will not work. And this, when it is reaching a limit of 1 volt and beyond that, it is in saturation mode. IC max and Vi minimum saturation mode, and in saturation mode we consider transistor working operation in on condition. Okay, and this is the active mode of transistor when current is linearly decreasing. Active mode. Okay, where current is linear. So these are the three mode of transistor in which transistor operate. First one is cut off, which we consider as off state. What is happening in this? Transistor is not started yet because the voltage is below 0.7, which is knee voltage for the transistor or cut-in voltage for the transistor. So the voltage is below 0.7, so that transistor operate in the off condition. Why so? Because IB current is not flowing, so that IC current is not flowing. If current is not flowing in the circuit, whatever the voltage we are getting in the battery side, we are getting at the output. So V out is nothing but the VCC, value of VCC, and current is not flowing in this section, so it is cut off. Now saturation region, what is happening? IC reaching its maximum value. Beyond that, it is not increased. So maximum value of IC we are attaining, and at this maximum value we are getting the Vi minimum or V out minimum. Sorry, the value of V out is minimum. So minimum voltage, but it is a steady voltage. So at saturation mode, we consider this transistor is fully working or it is in on state. Okay. An active mode of the transistor is basic operation mode of the transistor. Okay, we already discussed these active cutoff and saturation mode in our DC load line topic also, and few other topic also. So this is the topic of switching. So we are considering here only the switching purpose of the transistor, so that we are using common emitter configuration here and NPN transistor, and we have the cutoff region, which is nothing but the off state of the transistor, and saturation region, which is nothing but the on state of the transistor. So this is the whole operation in which we discuss the switching of the transistor. Hope you understand this topic, and we will discuss few more topic in our next class. Till then, thank you so much and subscribe.